Welcome to part 2 of the Curta calculator series. In this video, we'll continue exploring how subtraction is implemented, how to multiply large numbers using the carriage position, and other special mechanisms that made the Curta a perfect calculator. If you haven't watched part 1 yet, the link is in the description. Among the 11 result registers, 8 are connected to the input setters, and 3 are only connected by the carry mechanisms. But a count gear is fitted on each of the 3 transmission shafts at its 0 position. We will see why later in this video. The carry gear is actually made up of 2 types of gear. The lower gear is the same as the other count gears on transmission shafts, but the upper gear has an odd shape. Apart from providing support on the carry sensing lever, it is used to prevent accidental rotation of the gear shafts, and it is called a lock gear. It is specifically added to the first transmission shaft, which doesn't require a carry gear. To prevent accidental rotation of the gear shafts, 2 lock rings are added to the tens bell, meshing with the lock gears on the transmission shaft. The lock gears can only rotate in the cutout section of the lock ring, which aligns with the step drum's teeth region. This ensures that only the step drum can drive the transmission gears. Once the step drum passes, the lock ring locks all the transmission shafts from rotating. The second lock ring meshes with the lock gear when the carry sensing lever is in the down position. This lock ring has a slightly larger cutout to allow the carry gear to rotate 1 step before being locked. The turn counter works similarly to the main calculation mechanism, but uses a separate smaller drum for adding and subtracting. It has its own transmission shafts with count gears that engage with the step drum, as well as a similar carry mechanism with separate tens bells and lock rings. These lock rings are aligned with the angle of the step drum. The turn counter increases by 1 in addition mode. The step drum has only 2 rows of 1 tooth and 1 row of 9 teeth. When the Curta is in addition mode, the turn counter increases by 1, requiring only a single step rotation at the least significant count gear. The remaining count gears are offset and do not mesh with the step drum. As the turn counter increments, a carry is sent to the next transmission gear when the count passes 9. Thus, except for the least significant register, the rest of the turn counter registers are driven by the carry gear. Since the crank can only rotate in one direction, to decrease the count, the Curta uses a clever method called the tens complement. The tens complement of a number allows for subtraction by adding the tens complement, which is the number you get from subtracting from 10. For example, to subtract 1 from 1 to get 0, you add the tens complement of 1, which is 9. Imagine a numerical dial with 0 to 9. Adding 1 rotates the dial 1 step counterclockwise to get 1. Adding 5 rotates the dial 5 more steps to get 6. For subtraction, you can rotate clockwise. To subtract 1, you can rotate back 1 step and get 5. But it is not the only way. We can get 5 by rotating 9 steps counterclockwise as in addition. So subtracting 1 is like adding 9 counterclockwise steps. The step drum has 9 teeth to facilitate this subtraction method. In subtraction mode, the crank is pulled up along with both step drums. Now, the small step drum's 9 teeth align with all the count gears. You might think that rotating all the count gears by 9 steps would change the turn counter registers that were previously 0 to 9s. However, that is not the case. When we add 9 steps to decrease by 1, every number except 0 will result in a carry when added by 9. This carry propagates, rotating each transmission shaft by an extra step, turning all the 9s back to 0s. Now we understand how the turn counter step drum works for incrementing and decrementing. To reverse the turn counter behavior, a reversing lever is connected to all the count gears and can move them up or down. For precise positioning, the same ball and pit mechanism is used inside the lever. In addition mode, when the turn counter is supposed to increase by 1, pulling the reversing lever down aligns all the count gears with the 9-teeth section of the step drum, changing the turn counter to decrement mode. In subtraction mode, when the step drum's 9 teeth align with the count gears, the turn counter is supposed to decrease by 1. However, pulling the reversing lever down moves all the turn counter gears down, aligning only the least significant count gear with the step drum's single tooth, changing the turn counter to increment mode. Now that we understand how the turn counter works, let's return to our main step drum. We already know how addition works. The step drum rotates the count gears, and the tens bell manages the carry gears with the carry sensing lever. However, subtraction is a bit more complicated than the turn counter, which only needs to decrease by 1. Unlike other mechanical calculators, the Curta uses a single step drum for both addition and subtraction by shifting the drum to align with a different set of teeth on the count gears. Since the crank can only rotate in one direction, we need a way to subtract by adding the complement. Let's try to use the tens complement. To subtract 45 from 76, we add the tens complement of 45, which is 65, and get 141. We can omit the most significant digit, resulting in 41. The correct answer should be 31, but the extra 10 comes from the carry mechanism. The tens complement works without a carry mechanism. For instance, using multiple numeric dials, set the right 2 dials to 7 and 6, and add the tens complement of 45, which is 65. Add 5 steps to the 6th dial to get 1, and add 6 steps to the 7 dial to get 3. This gives the correct answer of 31. However, in the Curta, we already use the carry mechanism for addition. To compensate for the carry, we use the nines complement instead of the tens. This way, the carry automatically combines with the nines complement, functioning like the tens complement. Let's subtract 45 from 76 using the nines complement. Instead of adding 65, we add the nines complement of 45, which is 54. Adding 54 to 76 gives us 130, which is 1 less than the correct answer of 31. Let's try another example. Subtract 23 from 40, adding the nines complement of 23, which is 76, to 40. That gives us 116, which is 1 less than the correct answer of 17. And what about the most significant digit 1? Since the same carry mechanism is used, the carry will surely be sent, and the result will be 116. To solve this, let's add extra zeros in front of the numbers. For example, instead of 40, write with all the result register values 0, 0, 0, 0, 0, 0, 0, 0, 0, 4, 0, and for 23, write 0, 0, 0, 0, 0, 0, 0, 0, 0, 2, 3. When converted to the nines complement, all leading zeros become nines. The extra carry changes the result register of 9 back to 0, propagating the carry to the left until it gets out of range. So we get the result 16. Still 1 less than the correct answer, but we'll get to that. To implement the nines complement in the step drum, add the nines complement number of teeth to the step drum at its shifted position. For example, the input slider at 0 aligns with the 9 teeth, at 1 aligns with 8 teeth, and so on, until the input 9 aligns with no teeth. To add the extra 1 to the least significant digit, extend the least significant count gear to engage with the upper row, which is 1 digit higher. For instance, when subtracting 3, the count gear aligns with the 6 teeth, but the extended gear aligns with 7 teeth. solving the one less than problem in subtraction. At the 0 position, all the count gears are aligned with 9 teeth, except the extended gear section, which is now aligned with the 10 teeth. So even if you try to subtract 0 from 0, we will get the correct answer 0 because of that extra 1. Let's test the subtraction mechanism to compute 76 minus 45. First, we set 76 in the result register by using the addition mode, which requires pulling the crank down. We then set the sliders to 7 and 6 and rotate the crank once. To subtract 45, we change the mode by pulling the crank up. Next, we set the sliders to 4 and 5. At this point, gear 4 aligns with its 9's complement, 5, and gear 5 aligns with 4, while its extended gear aligns with 5, which is equivalent to the 9's complement plus 1. The other gears, set to 0, align with 9. When the crank is rotated, all the values get added to the result gears except for the extra carry, which is lost at the last register. The result register correctly shows 31. Now we fully understand the addition and subtraction operation of the Curta calculator. For ease of use, there are several mechanisms to prevent incorrect operations. To prevent the crank from rotating backward, there is a ratchet and pole mechanism at the bottom of the crank. The pole is tightened by a torsion spring and rides along the ratchet teeth. The constant clicking sound you hear when the crank is rotated comes from the pole striking the ratchet gear. If the crank is rotated backward, the pole and the ratchet gear tooth get stuck, preventing rotation. Since the crank rotates in the same direction for every operation, it's important to know when the crank is fully rotated. To address this, a circular disc with a semicircle cutout called the zero positioning disc is used, along with a zero positioning lever, which is a roller arm fitted with a torsional spring. This lever tightly rides along the arc of the circular disc. At the 0 position, the roller arm sits perfectly in the semicircle cutout of the 0 positioning disc. As the crank is rotated, the 0 positioning disc turns until the 0 positioning lever falls into place, providing resistance when the 0 position is reached. This lets the user know when the 0 position is set or if further rotation is needed. To change the mode from subtraction to addition or vice versa, the crank must be pulled up or down and should remain in position unless changed by the user. This is achieved using a clip spring, called the step drum positioning spring, which slips between two holes in the step drum's base cylinder. A certain amount of intentional force is required to overcome the positioning spring to change modes. To limit the range of the up and down positions, a small metal plate, called the step drum positioning tongue, is added to the base, and two metal flanges are added to the crankshaft. The up position of the crank is limited by the bottom flange, and the down position is limited by the upper flange. A small cam is added in between those flanges, and it allows the crank to move up or down only at the 0 position. At any other position, the crank can only rotate and cannot move up or down due to the tongue intersecting with the cam. Do you notice that even though the tens bell rotates along with the main shaft, it doesn't move up or down when the main shaft changes operation modes? This is because the tens bell shaft isn't directly attached to the main shaft. Instead, it is held against the upper main casting by a washer and a shaft lock ring. It rotates with the main shaft due to the tens bell locking pin on the step drum loosely coupling with the tens bell. At the top of the result registers and turn counter, there is a spider spring that forces tiny balls onto the gears of numeric dials. Similar to the balls inside the input sliders, these tiny balls prevent the gears from rotating on their own, maintaining the value at all times. If you look closely at the numerical dial gears, you will see some teeth missing. This design is for clearing the result registers and turn counters. The clearing ring has two gear racks that are slightly offset. Both of the racks are 9 teeth long, which is the maximum number of steps needed to rotate from 9 to 0. The clearing ring can clear only the result counters by turning through the black section, or clear the turn counter by turning along the white section. So the clearing ring can stay at this intersection or this intersection. In both of these positions, you can see the clearing gears are offset from the main gears, so that the main gears don't drive the rack and clearing ring. That is why there is an extra rack in the offset, and it will take care of clearing those offset gears. When the clearing ring is rotated, the gear racks mesh with the gears and turn them until there are no teeth to engage. This is why 2 teeth are removed at the 0 position. As the rack passes, all the gears rotate until they reach 0. A spring-loaded pin, known as the clearing stop pin, is located on the carriage body and pushes against the inner surface of the clearing ring. There are 2 grooves precisely aligned in between the result registers and turn counters, providing the user with tactile feedback of the clearing endpoints. The clearing ring can also be rotated inward when not in use, allowing the calculator to fit inside a cylindrical container. For multiplying with more than 1 digit, the entire carriage can be moved up and rotated up to the 6th position. To precisely move the carriage to each digit position, grooves are cut out in the direction of the carriage shafts on the underside of the carriage body. To see more clearly, let's separate those grooves. These grooves fit with 2 blocks located on the upper main casting, ensuring accurate positioning. To change the carriage position, first lift the carriage to release it from the blocks, rotate it to the desired position, and then place it back inside the groove. A small extrusion on the carriage body limits the carriage to stay inside these 6 positions. Because of the spacing between result and counter is slightly bigger than the spacing between each shaft, the result gears won't interfere with the counter gears. The carriage needing to move around is not fixed to the upper main casting. Instead, it is held down by a crank collar, along with spider springs, clearing rings, and a digit cover. Similar to the tens bell, the crank collar is secured by a shaft lock ring on the upper main casting, with a spring loaded between the crank collar and the shaft lock ring, creating tension when changing positions. Now let's see the genius of changing the carriage position. For example, to multiply 87 by 50, set the sliders to 8 and 7, and move the carriage to the 2nd position. If we closely examine the transmission shafts behind the input sliders for 8 and 7, we can see they are now connected to the 2nd and 3rd result gears, effectively turning the input 87 into 870 when we rotate the crank. Additionally, the count gear transmission shaft is now engaged with the 2nd digit of the turn counter, meaning each turn will represent a multiple of 10. By rotating the crank 5 times, we get 50 on the turn counter, and we get the result of 870 times 5, which is the same as 87 times 50. To simplify it a bit more, let's say 2,567 is multiplied by 487. That means 2,567 is added to itself 487 times. To be clear, we can write it like this. We can also write it like this. Now we reduce all the multipliers to single digits, and we can get 2, 5, 6, 7, 0, 0, by shifting the carriage to the third position. By doing so, shift the turn counter registers so that every turn increases the third register. Turning 4 times gives the result 2, 5, 6, 7, 0, 0 times 4 with the counter values of 4 hundredths. Then shift the carriage to second position. Now turning the crank will add the 2, 5, 6, 7, 0 to the result. So turning 8 times will give us the combination of 2, 5, 6, 7, 0, 0 times 4 plus 2, 5, 6, 7, 0 times 8, with the counter value of 80 added to the previous 4 hundredths, making it 480, and so on. Making the carriage movable like this is genius, and it just works perfectly. We now understand the ingenious and intricate mechanisms involved in the Curta calculator, created decades ago by one person. It's amazing that something so unique and modern-looking was invented so long ago. From its ingenious design by Kurt Hertzstark in the 1940s to its enduring legacy among collectors and enthusiasts, the Curta remains a testament to human ingenuity and craftsmanship. If you enjoyed this deep dive into the Curta calculator, please support us by subscribing to our channel for more fascinating explorations into the world of mechanical marvels. Your support helps us create more content like this. Additionally, if you'd like to support us further, consider joining our Patreon community. Your contributions will help us continue to bring you high-quality content and in-depth explorations of amazing inventions. Thank you for watching, and we look forward to seeing you in the next video.